Hello everybody, we're going to be working on Unit 9 today, and Unit 9 will cover Chapter 8. Chapter 8 gets us into kind of a new area inside of Python, so we're going to learn about a new set of structures that we're going to kind of build into our repertoire here. So if you guys remember working with lists just a couple weeks ago, and how lists are what many other languages call arrays, and how those structures are one combined structure that allow you to store multiple values of different types. And then you have a bunch of special methods and functions that you can use to manipulate those structures and do some really powerful things, really with a minimum of code. The people who designed Python were very forward thinking in this, and knew some of the limitations that were out there in other languages when working with more complex structures, and developed two additional structures that we can use in very creative ways to really kind of take the capability of lists to a completely different level. One of those structures is called sets, and the other one is called dictionaries. And when you use a combination of lists, sets, and dictionaries, and yes, you can combine them all together, you can build some really complicated structures where you can store just about anything in there in really unique kind of ways and do some crazy powerful things with a minimum of code. So I'm starting to see this like marvelous like mystery being unraveled here as I see how Python is the data scientist's tool of choice, and partially because some of the technologies that we're about to learn. I will tell you that I'm not going to be going all the way through this chapter. I'm going to be taking us up to a certain point, and then the homework will be related to those to that content. I could take it further, but frankly, you won't really need it in this course. But if you guys are in the data science program here at Gateway, we'll be covering some of the more advanced topics when you get into your data analytics courses out there at IMET. All right, so let's go ahead and bring the book up on screen, and I'm going to get to the beginning of the chapter. Let's see if I can navigate my way there, and start our discussion on these interesting Python structures. All right, so with Chapter 8, we have a bunch of different goals. First of all, we're going to learn what a set is and what a dictionary is and how to use them. You know, what the syntax is, how you can use some of the pre-built functions for them to leverage them, and why you might use this structure over something else. And I think that what you'll quickly see, and what a lot of I think modern programmers are seeing, is where we might use like an array in the past, or maybe like complicated sets of code to do certain actions. These two structures give us the ability to really kind of accelerate workflow in a lot of interesting ways. And if you really get into it and want to explore more, you can explore like the later two topics. So I'm basically going to be covering the first three topics here, if my memory serves me correctly. But here's kind of the impetus for this. So this is kind of interesting just to read this and think about it in this fashion. It says, when you need to organize multiple values in your program, you can place them into a container. The list container, that's the one that we've learned so far, is one that's provided by Python. In this chapter, you'll learn about two additional ones, the set and the dictionary, and then we'll show you how you can actually combine those. So if you want to read that, that's the part I'm not covering, and you can make some really complex structures. What's really interesting about sets and dictionaries is that they, how we did lists in multiple dimensions, like we did like 2 dimensions, and when you get beyond that, it's kind of really hard to conceptualize it. You can do the same thing with sets and dictionaries. And if you start thinking about the fact that a set or a dictionary is a complex structure unto itself, it gets really mind-blowing really quick. So in other languages, they tend to call these types of structures like array lists or collections or enumerations, things, those are the terminology pieces that you see. But I'm going to tell you that from what I've read so far and learned so far myself about this, that the Python approach is actually a little more powerful. And now I'm really seeing the picture very clearly as to why data scientists are all over it for managing large data sets and doing some pretty sophisticated things with it. So the interesting thing about this is sets and this concept really extends directly from mathematics. So whoever put this language together, like a lot of computer scientists, they have to take way too much math. And if you study math as a discipline, and it's really kind of an interesting discipline to study, and I think that it gets a really bad rap, frankly, because it's considered difficult, it's very theoretical and abstract, but you know what? Numbers don't change, folks. 2 plus 2 is always going to be 2 plus 2. There's not going to be like 2 plus 2 version 3.0, for example. That's not happening. But this concept extends from an advanced area of mathematics that's actually fairly brand new in development. So if you look at the history of mathematics, we didn't even have like calculus until I think the 1600s. Prior to that we had algebra and Pythagorean math. So square roots and unknowns, x's and y's, and a lot of it was really revolved around the Pythagorean theorem and kind of extensions of that. When we moved into the modern mathematical era and they started figuring out calculus, and that's where you take more complicated equations and resolve them over a range of possible values, and you can create some pretty complicated structure there. And the goal of mathematics always has been to really kind of explain what's happening in nature mathematically, because if you can explain it mathematically, then you can manipulate it, control it, and figure out other things about it. And programming extends directly from mathematics. And I think we've talked about that earlier in the course. But one area of mathematics that was developed within the last couple hundred years is called set math. So some of the concepts that you see here, and maybe you've learned about this stuff even when you were a much younger person in school, but this area of mathematics also leads to things like probability theory and statistics and concepts like that. But set math is a very interesting thing. So some of the terminology you're going to hear in this section is going to remind you of set mathematics that you maybe learned about but didn't think about it in that capacity. So let's take, for example, what they're saying here. So let's just read it. That's not a bad way to proceed. It says, a set is a container that stores a collection of unique values. So if you think about a list, right, where we have, all these multiple spots where we can store stuff, nobody said that I couldn't put the same thing in position 0 and then the same thing in position 5. Sure, if you want to do that, go for it. It's yours. It's your list. Do whatever you want. But a set is different. A set, all the values within it must be unique. The other thing that's kind of interesting about it is you don't access any of the stuff within the set by using an index value. Things are not indexed. And because of that, it gives it some special capabilities that make things really powerful with this tool. All right, so it says, unlike a list elements or members of the set are not stored in any particular order and cannot be accessed by position or index number. The operations available for use with the set are the same as sets in mathematics. And what are those things? Unions, intersections, joins, things like that. So because we're not keeping things in a particular order, we can perform functions on it computationally or programmatically much faster than if we use other structures. So if we use a list has to be traversed in a specific way. If we use a set's like whatever, and just does it. So it can be a whole lot faster. So they start with this really cool example, and I think this is a really nice one that kind of helps explain it. So if I look at the British, Canadian, and Italian flags, each one of them is a combination of colors. So the British flag is red, blue, and white. And I think the British say it in that order if you ever ask them. They don't say red, white, and blue. I think they say red, blue, and white. The Canadians, of course, are just white and red, and then the Italians are white, red, and green. So If you look at the flag is ordered and positioned and it has a design to it so the colors are all in a certain spot. But when you're just analyzing the color itself, you can actually create a set based on each flag, the set of colors that goes with the flag, right? It doesn't matter if I say blue or red or white first for Great Britain, as long as they're there. If I try to add another color to the mix, it can't be one of the ones that's already there, right? So maybe I could add a yellow to it, but I can't add red again. Red's already present. So the values that go into a set must be unique. And that's a really big takeaway. Okay, that's I think a critical piece to understand. So how do we actually create a set with code? Well, interestingly, we use a set of curly brackets to do that. So remember, for a list, what do we use? This is kind of a language universal almost. Square brackets. Square brackets are what we use for lists. So all it takes to create a set is the curly brackets. But notice that the values, even though they're going into the set in an order, I can't access them via the order. I can't say cast curly bracket 0 and get Luigi. It doesn't work that way at all. There's no index. Okay, they're all just thrown in there. So this is how I declare one, right? And since these are strings, they're in double quotes and separated by commas. Could be integers, it could be numbers, it could be other structures. And then that's where the mind bender comes. For right now, let's just think about strings and numbers. Is that all right? Okay. So in other words, the set cast contains Luigi, Gumbies, and Spiny, whatever that means. It says, alternatively, you can use the set function to convert any sequence into a set. So for example, if I did have a list of names, right? So we know this is a list because it does have square brackets, right? If I want to convert that, I can use the set function, so I can take any list and convert it into a set, and here's the provided that all the values inside that list are unique. Otherwise, it won't work. It will throw an error. Is that clear? It wouldn't work, right? All the values in the set have to be precisely. The other thing that you can do is if you take a string and you declare it as a set, it will actually take the string and split all the letters apart. And sometimes programmatically, that's a pretty useful thing. So unfortunately, you can't use a set of empty curly brackets to declare an empty set. I don't know why, but it just says so right here in the book. If you want to declare an empty set, you actually have to call the set function to create it. So you have whatever you're going to create is your empty one. So cast is going to be our empty one. We have to run set empty parentheses, and that creates an empty one that we can then add stuff to. The other point it makes is, as with any container, you can use the length function on it. Just because we don't have an index on it doesn't mean that we can't determine its length. We can still count the number of things that are in there. So if I ran length cast, right, the number of characters, and I was looking at this, what would it return? 3. That would be the length, because there's 3 cast numbers. All right. Right. And even if we were doing the length function on a list and there were 3 things in there, it would still return 3. But the index values are 0, 1, 2. See the difference? Right. All right. All right. The other thing that you might want to do is you might want to determine if something you're looking for is in that set. So that's what this if statement is about. So it says, if Luigi in cast. So if Luigi is a member of the set cast, then give us a message. Otherwise, give us a different message, so that you can actually check to see if it's present. So you can look for something inside of there. You're just not doing it with an index. You're looking for the actual value, right? So if you're looking for a specific string or a specific number, you can search for it. The other thing that you can do is you can also loop through it. So in the next example, it says, because sets are unordered, you can't access the elements by position. So you can't like take a loop, set up an index value, and go number by number. However, you can still iterate over it using the for each approach as demonstrated here. So it says for character in cast, print character. So it would actually go through each individual entry in the set or member of the set and then output it. It's really simple to do. It's not very tricky syntax. It just does not work with index numbers. That's really the only difference. And so if I was to run this command, it would give me output, but the output would not necessarily come back in any particular order. In fact, you can't really predict what order it's going to come back in. You might think it would come back in this order, but it might just come back in the order that they showed here, which is just the opposite. You really don't know, and it's actually a jumble of it. All right. Now, if you did want to sort it, you actually have to run a method, or excuse me, a function to do that. So you have to actually tell it to sort the values, and then it will treat them in that capacity. If you wanted to do them alphabetically, you just throw that method at it. Kind of interesting, I think. All right, let's move on. All right, so you build the set. One thing that you might want to do is add stuff to it. Right, so you got a cast of characters for a play or a TV show or a movie or something, and all of a sudden you hire another person, right? So if I want to add Arthur to the mix, I just call the structure, and then with using dot syntax, I just say dot add, and then inside the parentheses, whatever it is I'm adding, and then that's added one at a time. So if you could think of like a program that you might write where you might put a prompt inside of a loop, you might say, who are the characters of the play? Press enter, enter the next character, type it in, press enter. You can keep going, and you could do an add each time, and you would build up your cast. So they have a little example here in terms of a graphic. So we started out with Luigi, Spiny, and Gumby's, and then we added Arthur, right? So we did add Arthur. We did add Spiny. Would that work? No. Spiny's already in there. So, and then notice if I want to get rid of one, what's the command? Discard. So this command wouldn't work. Just won't allow it, right? All the values in the set have to be unique, and that's kind of an important little thing. So that's how you do add, and then that's how you do discard. So this one would work if I had already added Arthur. Then they make the point here, if I say discard the kernel, has no effect because there is no kernel in our set. The other thing that you can throw at it is the remove method. And the way that these differ is, if it's there, it'll get rid of it. But this will also throw an exception. And of course, we learned a little bit about that last week. And sometimes you intentionally do that. You throw an error message to drive something else in the program. So just keep that in mind. There's also a method called clear. And what clear does is it takes that whole structure and just gets rid of all the content inside of it. So with a set, we can add, we can discard or remove. Discard has no exceptions, remove does. Then we can do a clear to get rid of everything. And those are probably some of the more useful ones because those are common actions, right? Add, remove, and clear it out. So those, I think, are all very useful. All right. Where it gets interesting is this, and this might trigger some stuff inside of your brain somewhere, because if you ever learned set theory in mathematics, you've also learned that there's this thing called subsets. So let's take a look at what that means here. And you know what, let's start by reading what the author says. He says, a set is a subset of another set if and only if every element of the first set is also an element of the second set. So that's a really fancy way to say that if I look at the colors for the British flag, which are blue, white, and red, then I look at Canada, which is red and white. Red and white is a subset of the British flag, right? And that's not by mistake. Many British colonies have those same colors in their flags, which is kind of interesting. So this is what we would call a subset. So the Canadian flag would indeed be a subset of the British flag. Kind of weird, all right? Why is that useful? Well, it might be. It depends on what you're doing. Another thing that's kind of interesting is this. We look at the Italian flag, which is in this circle, and that's red, white, and green. Now, while two of the colors are part of the British flag, one of them is not. So this one is not. The Italian flag is not a subset of the British flag because they have one color that's different, which is green. So you see how that like doesn't fit inside. And I think the visual really helps explain that pretty well. All right. So they do have a method called is subset, and you can think of it as kind of like a question, right? And it returns true or false. But if we went ahead and defined the Canadian, British, and Italian flags with their colors in the forms of sets, then we can run methods that say if Canadian is subset British. See how that reads? Right? And I like that because it's almost like an English sentence. So if the Canadian is a subset of British, which it is, then it would print this message. All Canadian flag colors occur in the British flag. Okay. Then look at the Italian one and look at the logic here because they have a not. Okay. It's saying Italian is subset British. We know the answer to that is false, but we put the not in front of it, which flips it to true. So that statement's true also because it is not Italian subset of British flag. Hopefully you can see the logic there. Now, let's throw into the mix that, you know, the Americans aren't the only ones with red, white, and blue. In fact, the Russians are too, right? That really confuses things. Like the old days when they were a completely different color, we could just call them reds. You know? Yeah, because they're red, white, and blue too, right? But okay, so the French have a red, white, and blue. And then the point here is, in that bottom example, is that you can also check to see if the sets are equivalent. So even though the colors might be listed in a different order, so if you look at British, it's red, blue, and white. And then if you look at the French, it's red, white, and blue. Is British equivalent to French? Yes, they are. It doesn't matter what the order is. They have the same elements. It doesn't matter how you shuffle them up, right? It's like a deck of cards. You can shuffle it, but all the same cards are in there, right? So you can actually check it for those kinds of scenarios. All right. Let's add a little bit more of this set theory into the mix here. So some of this might maybe trigger a bell somewhere in the back of your head. So let's look at what we call union, intersection, and difference. All right. So it says the union is when you take two sets, regardless of if they have common elements or not, join them together and create one new larger set. So for example, you can do that in Python by just calling the set names and then throwing one of them into the function that forces them to join together. So in the first example, it says British.union, and we throw Italian in there, right? So we're going to take the red, white, and blue, combine it with the red, white, and green, and we end up with blue, green, white, and red. We don't get two blues and two reds, you know, or two whites and two reds. But the joining of those two now adds green to the mix in a brand new set. That's called a union. The funny thing about the union is you can kind of actually declare it both ways, right? So this is the union, right? And I don't know how it appears on your screens where you guys are seeing it, but they're showing that the circles are combined, so all the colors are the same between all three sections there, even where they overlap. And that's called the union of two sets. If we are doing what we call an intersection, then we're looking for the stuff that they have in common. Right? So that's a different approach. So that command is intersection Italian. So we say British dot intersection Italian, and then we end up with what? The ones that they have in common, as opposed to joining them all together. So you can see how that might be useful, right? You might have to ask a question like, what things do they have in common? You could do an intersection on a set and figure it out. So that's displayed here in this image. Then we also have the difference, right? So depending, and the difference is kind of weird. This is kind of fascinating because I could say here British intersection Italian, but could I also say Italian intersection British? Sure, I get the same result. Doesn't matter which I put first. When I do this last command, difference, that one will give you a different result depending on your order. So I think that's pretty important. So for example, if I'm looking for, it says colors that are in the Italian flag, but not the British, I would say Italian first, and then the difference with British. And it says, well, the difference is Italian's got green, so it's going to output green. See the difference? And then if you flip it the other way, the difference you'll find is blue for British because you're looking at it from the British perspective as opposed to the Italian. It's like, what do we have in the British flag that's different than the Italian flag? Is, well, we have blue. They don't. So this graphic basically shows that depending on which order you ask it in, you will get a different result for that one. So that one you have to kind of know in order to figure it out. Here's a whole listing of really common set operations, most of which we've talked about already, and a few others that we haven't, but I think that the ones that we haven't, you'd probably pick up really, really quick. All right, let's move on. Now here's an example that they're giving us that is going to be, I think, useful for our homework, and I'm just pointing that out right now. But this is what they call one of their worked examples. So they set up a problem, and in this case, they're looking at Mary Had a Little Lamb, the nursery rhyme one more time. And the point of this exercise, and this is a practice exercise, is to read in the text file, count the words that are unique. Now, if you think about how you would do something like that, if you parse through a text file and read in every word, and as you read in every word, you add it to a set. If it adds, it's unique. If it doesn't, that means the word's already there. So a word like and, the, of, so, whatever, those real common ones, you know that those are going to be, not be added. So as it reads through, it figures out how to do that. Just keep adding the words to the set. If it adds, great. If it doesn't, and then at the end, all you have to do is check the size of the set, which you do with the length function, and you have the number of unique words. If you want, you could also output them, right? Because they're already in the set. It'd be really easy to do. So you see, like the procedure for that is not really that difficult, and they walk through and they have an example. So this is very useful for the homework we're going to attempt here in a little bit. All right. I have a couple of little tips and whatnot here. I always like to read through these because I think some of them are pretty important. And this one says, use Python sets, not lists, for efficient set operations. And this is a little bit of a mindset change, including for a person like me, that my whole life I've worked with, arrays and other structures like that where we do have indexed values. It says, when you write a program that manages a collection of unique items, sets are far more efficient than lists, and some programmers prefer to use the familiar list, replacing something like this, item set dot add item with, and notice what they're doing in the second statement. It says, if item not in item list, then we add the item. That's kind of weird, right? So if I had a set, here's the point of this. All it takes to add something to a set and ensure that it's unique is just to issue an add command or function. If it's not there, it adds it. If it is there, it won't. Just as simple as that. With a list, before I could put something in and make sure it was unique, I'd have to check to see if it was unique first and then insert it. So that's actually 2 or 3 operations when I start to think about it, and it's significantly less efficient programmatically. Not a problem if you're reading in a couple of things, but if you're reading in a list of like 10,000 things or a million things, you're talking about a significant change in processing. Significant change in how it processes and how quickly it works. So this is kind of a fascinating little point that he's making here, and I think that's really, really cool. All right. Another thing that is really kind of special about Python is you have to start asking yourself, right? With a list, I understand that if I start putting stuff in there, I think of it like my Excel spreadsheet that I showed you guys, where we would put stuff in there, we would number each one, and then every time you add something, it just kind of adds it to the end, and we increase our index values. Somehow, Python is still keeping track of what's inside these sets and organizing them. And the technique that they use is this process called hashing. So I think that this is really kind of an interesting read. I would really strongly suggest you guys read this section. And I, might even throw a test question on the final about it. I'm just saying. But if you were to look at a set of books on the shelf, and I like the example that they're using. I think it's a good example. And sometimes when you like take a collection of books, and let's say they're all unique, and you want to put them on a shelf, how do you organize them? You just like throw them on the shelf? Do you even make them sit upright, or do you go sideways with them? And then sometimes, like when you're putting books on a shelf, sometimes you take the tallest ones and you put those together, or the thickest ones together, or sometimes it's like the topic, or like in their example here, they got some with white spines, some with blue spines, some with orange, one's black and red, right? And how Python keeps what it calls a hash table, which whatever way it determines it, and they actually explain how they determine it, it's all done mathematically, is the hash is taking like whatever the representation of the item is and turning it into some sort of numeric thing that then can be sorted by Python in some really weird way. That's kind of like the equivalent of like sorting by color or size or height that it does kind of intuitively. And then that hash table that it creates is really kind of the index, but it's not something that we can necessarily manipulate unless we understand how it's being generated. And that's really kind of a strange thing. Anybody that's into downloading software and wants to verify the integrity of the file, Tom, you probably know what I'm talking about, right? You download do you ever go to a website and you download a program and they provide like a hash string that you can run special pieces of software that compare it to the file that you just downloaded to make sure that that's actually the file you're downloading? Yeah, because otherwise you could be on a hijacked site and you're downloading something that doesn't match up with the hash. And the hash isn't the file, it's just a numerical representation that makes sure it's the right file. And it's the same way that this works. It's really kind of, yeah, I mean, that's basically what it is. It's just kind of looking at it. They go through and they explain how it works here, and if you really want to dig into it further, you can research it. But I think it's a fascinating topic. The other one that they get into here is this whole concept of standardization, right? Whenever we work with a language of any sort, of computer code, how well a language works really often is because of the standardization on that language. So for example, why do we have the powerful web world that we have now? Because a number of years back, they said, okay, well, they got this thing called HTML now, or creating web pages. Well, maybe if we created a standard for it, then everybody could write their browsers around the standard. And so it doesn't matter what browser you use, you can get the same content the same way, and it works right, right? And believe it or not, it wasn't that long ago. I mean, I'd say 5 years ago, where it was like so unstable that depending on how you wrote your code and what technologies you used and what browser you used, what operating system you used, you could get radically different results. It has gotten so much better in the last 5 years, and we thank basically the W3C and HTML5 for being a standard that has allowed that to happen. The point that they're making in this little blurb is that Python, unlike some other high-level languages, has not been standardized yet. which is really pretty bizarre considering how popular it is and how quickly it's growing. And they talk about it in detail, but there are some other high-level languages, um, like C++, for example, and that one's been around for a really long time, that is standardized. And what that means is when you write C++, regardless of where you write it, that code will work on any other platform where C++ operates. Believe it or not, there are many languages that don't do that. They're written different across every platform, and really leads to a lot of problems. For whatever reason, Python hasn't been standardized, but people seem to have followed kind of like certain conventions. And generally speaking, it works the same on every platform to this day. But I'm really curious to see if at some point it gets like that huge that they actually write a standard for it. We'll see. All right. Let's move on to the next topic here, and that is dictionaries. So we learned about sets. We kind of started wrapping our minds around that. It's not really that big of a deal, right? It's not that hard to really fathom. And then we throw in this other container structure called a dictionary. Now let's take a look at this real carefully. I'm going to read once again what the author says here to start with, and then I'm going to give you my take on it. So it goes like this. It says a dictionary is a container that keeps associations between keys and values. Every key in the dictionary has an associated value. Keys are unique, but a value may be associated with several keys. All right. All right. Now, let me just throw this in right off the bat. So right off the bat, what you're doing is you kind of have two structures working together here. So you see how they have the two circles shown. So for every value that you want to store, so look at the flag colors, right? So we have red, green, and blue. In order for me to store it, I also have to have a key value that matches each individual one. And what this is indicating to you is that all the keys must be unique, like a set. In a set, all the values must be unique. However, it's possible for one of the values to be attributed to more than one key. So here's kind of a way where you can use something kind of like a set to store values, but not necessarily have to have all your values unique. The key is what's keeping it unique. And in many languages, we talk about this structure. In some languages, we'll call these associative arrays. And so what that means is they're not indexed by number. They have key value pairs. So for every piece of information you're storing, there's a key that goes with it. Sometimes that's an ID number. So if you think of like a database, for example, you have an ID number and then the value. Here, everything goes in pairs. So that's kind of interesting. So keys must be unique, but values don't have to be. I think that's really the big concept here. No. All right. So let's take a look at this example of what a dictionary looks like relative to a set. So the first line here is a set, just like what we did in the previous section. So we define a set, we got our curly brackets around it, and then inside there, we just have our comma-separated values. Right? They're all unique. In a dictionary, we combine the key and the value together. So for each item, we have the key value, Romeo in this case, separated by a colon, and then the value itself. So I don't know what this is. Maybe Romeo's favorite color is green, and Adam's favorite color is red. But those two things will always travel together. And here's the interesting thing about it. Because we have keys, we can use the keys to look up the values. Or we can look up values and find the keys that are associated to them. So a nice way to think about this is maybe like if we had like teams, right? Or if like I look around the room here and we have like 4 student pods of desks, right? And David, you're in like pod blue, right? So the pod might be the key and you might be the value. Just to give you kind of an example. And really, we're associating it. Now, if you do want to declare an empty dictionary, this is why you can't do it for sets, because when you use an empty brackets, it's actually creating an empty dictionary. That's why we can't use it for sets, just by the way. All right. The big takeaway here is that dictionaries are a combination of key-value pairs. Once again, other languages will call these associative arrays. It's considered kind of an advanced concept, but it's not really too weird. All right, so let's say you want to make a dictionary, and you want to make that a dictionary that looks up phone numbers. Sounds like the contact list on your phone, right? You put in a person's name, and then you can associate to that person's name their phone number. So when you start to type a text message or a phone call and you look up the person's name, it'll start narrowing down and then find that particular value that goes with Fred, for example. So they have a dictionary here called contacts, and then inside the curly brackets with key value pairs, the key is Fred, the value that goes with it is this. I'm not sure how that's, oh, I guess it's a 7-digit phone number. I used to remember those. We don't even think about them as 7-digit numbers anymore, do we? But each one of these, so Mary's number is this, Bob's number is this, Sarah's number is that. If you want to think of it as a structure, this structure is a good example. But each key, which must be unique, must have the same, must have a value attached to it. Do you guys notice that Bob and Mary have the same phone number, so they must share a cell phone or something, or live in the same house? So that's allowable in a dictionary. Kind of interesting, if you want to create a duplicate copy of a dictionary, you can use the dictionary function. So it's just the first 4 letters, throw in the structure that you have, and then it creates a copy. Sometimes, before you manipulate data, sometimes it's not a bad idea to make a copy of it first. Now, if you think about how I teach you guys programming, if you're working on a large program in a class, I always tell you every time you start working on it fresh, you always make a version. That's kind of how you do it with the dictionary. Make a copy of it. Pretty simple code to do it too. All right. So how do we get this stuff in a dictionary? Well, that's a little bit different story. So we actually have to figure out a way to traverse the structure. And if we wanted to find what is associated with Fred in the contacts list, notice the syntax. I use square brackets, kind of like an array, right? And then instead of looking for a number, I'm looking for the key Fred. So if I say print Fred's number is, and then I run contacts with Fred in there, square brackets, it will output his phone number. So it looks up Fred in the list, and it's like, okay, I found Fred. Here's the value that goes with Fred. Let's output it. Which is kind of like the equivalent if you were looking at a list and tell me what's in index position number 3, and it outputs what's in that position, not the number. Get the comparison? So really, in many ways, a dictionary is kind of like a list, but you're not using index numbers, you're using key values. And once again, in other languages, we call this an associative array. All right. So they do have a number of different things here that they look for. So if you want to check to see if something exists in your dictionary, you can just do a simple if statement like this and just check to see if a certain key exists in the dictionary. And then if it does, you can output it. Otherwise, you can send out an error message. Sometimes it says you want to use a default value if a key is not present. So, for example, if there's no number for Fred, you want to dial the directory assistance number instead. All right. So what they do is you issue the command called get, and that looks for Fred. And if Fred's not found and we don't get back his number, then call 411. And that's directory information if you didn't know that. That's if there's no matching key. If there was a matching key, his phone number would go into the number. Hopefully that makes sense to you. All right, what if you want to change the value associated with a key? It's pretty simple. You can just simply, just like you would with a list and an index value, you just declare which key you want to change and the value you want to go into it. Simple as that. Might be the same, might be different, but this would overwrite what's already there. And so they give that as an example here in the graphic. So John started out with one number, type in this command, and we start sort of the 222 number in there, and then after step number 2, that's what's in the dictionary. Pretty simple, really. Not that difficult to do. So if you want to go through and create an empty dictionary and then one by one add key value pairs, you would do it just like this. That's one way to do it. All right. If you're interested in perhaps removing items, now remember the terminology. Remember this terminology, pop? We talked all about that, pop and push. So if you want to pull Fred out of the structure, you pop him out. So when you pop Fred, Fred will be removed and the value associated with Fred. So you're not just taking Fred's name off the list, you're taking his number off the list too. If you compare that to how your contact list works on your phone, find your friend's name, delete, he's gone, number's gone, anything else you got stored with it is gone too. All right, that's a pop. That's to remove. If you want to like step through a dictionary and you want to basically do what they're calling traverse or iterate over the structure, you can do that like this. So you can say, notice key in contacts, key indicating the key value. So for each key value, print the key. Because how are you supposed to know what's in there? Maybe you don't know what's in there, right? So if you read in, let's say, an external file or database or something, how do you know what values are there? So you might want to run a routine like this just to show you what you put into the structure. That's kind of interesting. And it's kind of, notice a little note below it. It says, note that the dictionary stores its items in an order that is optimized for efficiency, which may not be the order in which they were added. Because as a computer's running, sometimes memory spots open up that were previously filled. And it might be more efficient for the computer to use that spot that just opened up rather than at the one at the end of the list. So we make this naive assumption thinking that because we're dealing with one location in memory that can store a bunch of stuff, that all of it's in the same spot in memory. You know, it might not be. It could be all over the place. That's why a computer will run much more efficiently if you don't overload what's in RAM. Or if you have more RAM on the system, it will work that much more quickly because everything's together and there's plenty of space to move things around. All right. So they can also say that if you wanted to find the value that's associated with a key, you can also, like for example, if you were to do an output statement like this that's formatted, you can find the key and then output the value of the key very much like this. And then that would output a list just like this. So it would display the key and the value. Can you do it the other way around? Yeah, you can flip it around. Just switch the two arguments. Not a big deal. Right, and then they make the example here if you wanted that list sorted. In this case, they would be sorting the key, and then it would actually put them alphabetically. All right, and they have a few other examples here. If you wanted, it says here, you can also iterate over the values of the items instead of the keys. So you don't have to iterate over the keys. We can actually look for the values. And if you're going to do that, this is what you have to add in your loop statement. So you're going to iterate through the values, not through the keys. And then if you want to add numbers to it, that's what this is doing here. All right. And I think that's enough of an example for you guys, frankly. And I forget what section comes next. All right, so they talk about iterating over dictionary items, and we're going to look at that as we kind of do our exercises. So I'm not going to spend too much time on that. I do want to talk a little bit about this though, and that is this structure that you see here, right where my cursor is, where you can put in records like this. And some of you, and I don't know what your programming background is, but as you guys move forward into your next semester, and you start to take your JavaScript class, and as you start to take higher levels of Java and all the other languages you're going to learn, you're going to start to see what we call serialized data like this really often. And like, for example, if you're working with JavaScript, we would call this a JSON string. And it's no surprise that Python supports this because it's basically that. And what it means is all your data is serialized. It's inside curly brackets. It's in key value pairs. And if you look at what's happening here, it really is kind of the definition of a data record. Think about that, right? So I have an ID of 100. The name is Sally Roberts. The class is 2. The GPA is 3.78. That sounds like a database row of a table in a database. It's exactly what it sounds like. And you know what? That's how a lot of that stuff is done, is using serialized data like this. And it's become a really popular format, especially when you see it in JavaScript. We write applications that feed back that kind of data or that create that kind of data because it's really easy then to feed it into just about any type of storage mechanism or any type of database or into a file or output to another application to manipulate live and do something else with it. It's really kind of a powerful thing. And what they're indicating here is by using records like this, individual records, you can actually build up a data store or really a database just using these really simple commands. And I think we talked about this a little bit, so I think it's a really fascinating little thing to study, frankly. There's some other interesting thing here too, where they talk about how text messages are translated. So I mean, I'm sure you guys probably like use little kind of like shortcuts when you do text messages. You know, I'm one of those geeks that likes to do complete sentences with punctuation and proper grammar, even in text. You know, my wife will be yelling at me on text, and I'm like, "But dear, comma, I meant to take the garbage out. Period." And maybe that's not the case for you, because I know a lot of people abbreviate, and, you know, but they have a little example here of how you could take a bunch of stuff that you normally would type into a text message and auto-translate it. You got to be always careful with that kind of stuff. All right, and then we get to this section here, and this is where I am capping it. So I'm not going to go into complex structures aside to say this. Because sets and dictionaries are what we call complex structures, we are allowed to store other complex structures into them. That's kind of mind-blowing when you start to think about it. So I can have a dictionary that stores dictionaries, or a set that stores dictionaries, or a dictionary that stores sets, which then stores dictionary. You know, you can do all this like really weird, like if you can imagine it, you can do it. It's really more about the imagination of it than anything else, right? Now, I would encourage you to read through that. If you are in the data science program, we'll talk about this later. If you're not, if you're just in the programming track, this might, you know, be as far as you need to go. But chances are, if you ever do any really complex work programming with complicated organized data, you probably will need some of these structures to make stuff work correctly. And it's more about conception than anything else. All right, this finishes the lecture portion. We're going to take a short break here in class. We're going to come back and code. We got almost a good 45 minutes. We should be able to get most of it done.